All right, how's it going, everybody? So this video is titled Arithmetic and Exponent Rules. So, learning targets, number one, there's going to be two kind of quote unquote rules that I'm going to teach you. But what I really want you to understand is not like memorizing two rules, but I view this much more as making sure we understand basic arithmetic. And the thing about algebra, and I've probably said this before, is that so much of like learning algebra is just making sure you have good number sense, making sure you understand the arithmetic, and then all the algebras kind of drops out of, you know, the same things that happen with numbers, right? Having good number sense. So learning target one is going to connect arithmetic to these two rules. You should be able to use the rules to rewrite expressions using variables or numbers. And then lastly, we'll close by describing the connection between these rules and the order of operations. Okay. So, to start, as I just mentioned, the two rules we're going to talk about, I don't love teaching rules here. But this really view this more as a lecture about arithmetic, making sure you understand the arithmetic. Because then the thing is, like, once you understand that arithmetic, there's no need to like memorize a rule. It's like silly that it's even called a rule in some ways. But, and I want to point out, like, okay, why am I teaching these things? Well, one, of course, is just to make sure you have that number sense, the arithmetic part. But two, we're going to do a lot of stuff where we apply these ideas. So they're more than just rules. It's like you need to be able to understand the arithmetic. And then once you understand the arithmetic, we can actually apply it, right? So we'll look at applications of how you use these things, just not in this video. So that's what we'll do in class. Or throughout this course, right? So for now, I just want you to understand the arithmetic, and we'll see how these things are applied. It's really actually quite remarkable how these two simple rules show up in a lot of applications, because they seem kind of like almost too obvious to be useful somehow. But I guess maybe the reason people decided to call them rules is because they were like, wow, these things show up in so many places and so many applications that maybe they deserve their own page in an algebra textbook. So anyway, my hope for you is to here just understand the arithmetic, and then we'll look at why it's useful throughout the course. Okay, so speaking of arithmetic, right? So going back to like elementary school or probably elementary school, whenever you learn this, I wanted to point out that the basic arithmetic operations you learn come in order. There is an order to these things, right? So an exponent or a power, right? When you're just talking about whole numbers, right? You learn this typically to start as repeatedly multiplying or repeatedly dividing. So make sure you've watched the video with negative exponents if you're not comfortable with this idea of repeated division. But as a refresher, repeated division comes from a negative exponent. Repeated multiplication comes from a positive exponent. Okay, but exponents then build off of multiplication and division. So notice there is an order. The exponents are defined in terms of the multiplication and division. And multiplication is defined by repeatedly adding or subtracting, at least when we're talking about whole numbers. So in elementary school, this is typically how people learn it, right? You see multiplication, 3 times 2 is 3 plus 3, right? I made two groups of 3, right? Multiplication is repeatedly adding or subtracting. And then adding and subtracting is really like first grade or kindergarten is just how do I count something, or preschool, whatever. Okay, the point here is that there is an order to the arithmetic operations, and this order is exactly the same order of the order of operations, right? Of course, I didn't write parentheses here, but understand that mathematicians, when they decided what the quote-unquote order of operations should be, they just said, hey, the arithmetic's already in order. Let's just keep that order. Keep exponents at the top, followed by multiplication, division as the second spot, and then addition, subtraction as the third spot. So please excuse my dear Aunt Sally, if you understand the basic arithmetic, like it's then becomes sort of, oh yeah, like that makes sense. I could see why they would just keep the order as is. Okay, so here's the thing. When you understand this sort of elementary school basic level of arithmetic, you can now get the two rules that I'm about to describe. So here's the first one. Let's say I have the function x squared and I multiply it by the function x cubed. My claim is that what you get, the result of multiplying these two things, is the function x to the fifth, right? So why does this have to be the case? Well, just use the elementary school arithmetic, the recursive idea of a power means repeatedly multiply, a positive power. So if I draw it all out here, x squared means multiply x by itself twice. X cubed means multiply x by itself 3 times. And lo and behold, how many x's in total do I have? Well, I have 2 from the first thing and 3 from the second thing. So I get 2 plus 3, or x to the 5th, right? Because you're just saying how many x's are there? I'm multiplying them all together, and you're multiplying together 5 x's. So that's why x squared times x cubed is x to the 5th. And that's the whole first rule. It's that easy. If you just think, okay, what does elementary school arithmetic say I should do here? It says I should take 2 of the first one and 3 of the second one, which gives me 2 plus 3, or 5 in total. Here's the rule written with just all variables. Okay, if it's x to the a times x to the b, well, the x to the a says take a x's, the x to the b says take b x's, and so you get in total a plus b x's, right? And of course, if you plug in any number here, you'll get a statement with arithmetic, which would look exactly the same. Okay, but that's the whole rule. That's the first one. I can do it again with subtraction, and there's a slight extra step you have to take here, but it comes from just understanding what a negative exponent is, right? So we just did x to the a plus b over here. What if it was now x to the a minus b? Well, nothing really changes. Adding is the same as adding the negative, right? So I can use the first rule again and just say, look, it's x to the a times x to the minus b. But if you understand that x to the minus b really means divide by x multiplied by itself b times, so it means divide, right, that negative exponent, then you can rewrite it a little more cleanly like this. X to the a minus b is x to the a divided by x to the b, for the reason that, again, x to the negative b means divide by x b times, right? So again, nothing really changes here, except when you throw a negative in, you have to account for the fact that a negative exponent means divide. Okay? So that's the whole exponent rule 1. Now let's look at exponent rule 2. Here's the second rule we need to understand, and again, just use the sort of elementary school arithmetic idea. This rule is now taking powers of exponentials. So if I have x squared and I cube it, right? So I have the function x squared and then I cube that function, I claim I get the function x to the 6th. Okay, so why do I get that function? Well, just ask yourself again, what does cubing something mean? Well, if I cube this thing, it means multiply by itself how many times? 3 times. And if I multiply x squared, here we go, by itself 3 times, each of those x squareds now gets its own spot there. There's 3 of them. But each of those x squareds is worth 2 x's, right? X squared means x times x. This x squared is x times x. And the last one, x times x. And so again, ask yourself, how many x's do you have in total? Well, it's 3 groups of 2's, or 2 plus 2 plus 2 is x to the 6th. And so there's the second rule written out. And again, it's just understanding taking a power as repeatedly multiplying in this case. Okay, so I can rewrite it now using more variables like I did last time. Instead of a 2 and a 3, if it's an a and a b, well, again, just think you're taking b groups of a, right? So if you were to write this out, you would do x to the a b times, but each of those x to the a's is a, so I have b groups of a each. So a times b is what I'm getting. Again, if it was a 2 and a 3 like we just did, you get 2 times 3 is 6. Okay, but that's the whole rule. I'm going to do just like last time. What if this was not a multiplication but a division? Instead of a times b, what would I get? And really nothing changes. X to the a divided by b, you still have this idea of it's like a power of a power, except now just you can rewrite divided by b as multiplied by 1 over b. Okay, so pause to make sure that makes sense to you if you need to. But, the basic idea is just saying I could say divide by b, or I could say multiply by 1 over b, and this is really the same rule as we had here, right? If this is x to the a times 1 over b, then the a would be here and a 1 over b would be there, which is exactly what I have, right? X to the a times 1 over b, or a over b, it's the same fraction. Okay, so there's the second rule. And I point out here, so I've been using whole numbers the whole time and using that sort of logic, but mathematicians basically at some point decided, well, what if the exponents aren't whole numbers, right? So there are reasons for this. And we'll look at this more in detail in class. But what if the exponents aren't whole numbers? Well, they decided that all the rules should really still be the same. So instead of an x squared and a cubed, what if I had something like a 5 to the 1.2, right? Should this really change anything? And the answer is no, it really shouldn't change. So if I draw this thing out here, I'm going to use exponent rule 1, right? This is like sort of saying, you can kind of think of it like saying 1.2 fives, and this is 6 fives. But in any event, I'm going to write this as 5 raised to the 1.2 plus 6, right? And certainly 5 raised to the 1 point, this is using rule 1, 1.2 plus 6 is 5 to the 7.2, right? So this all checks out. Okay, just using that, remember before it was an A and a B, and then A plus B, but like nothing is really changing here if I use decimals now in the exponents. Okay. Here's another one. If I take a power of a power, then remember I'm going to multiply, right? So again, the rule was x to the, sorry, that's kind of ugly. The rule was x to the a raised to the b, and that means you're taking b groups of a's, or x to the a times b, right? And so same thing here. If I make this 5 to the 1/2 times 6, and I do the arithmetic there, 1/2 times 6 is 3, so I get 5 cubed. And so I've applied rule 2 to make sense of this. And if you go to your calculator and you type in 5 to the 1/2 all raised to the 6, you will get 5 cubed, or 125. Okay. So to kind of conclude here, you should be able to do this with variables or numbers, use these rules. Each of these rules, and again, I hardly like to even call them rules because it's just sort of following your nose from what you already know from recursive arithmetic with whole numbers, multiplying as repeated, adding and subtracting, powers as repeated, multiplying and dividing. We talked about the relationship to the order of operations at the start, and I'm going to close this video with looking at these rules again in connection to the order of operations, because it's really neat. It kind of like everything all ties together really nicely into this sort of pretty little system here. And here's what it looks like. Here's how I would term this. Exponential functions, quote unquote, go up the order of operations if I write them like this. Okay? So remember the order of operations, the exponents on top, multiplication, division in the next row, and addition, subtraction at the bottom. Okay? But let's look at our first rule. Here it is in blue. X raised to the a plus b. Notice that I have a plus inside of the exponent. So there's my addition. Okay, so this is we're starting sort of at the bottom level, x to the a plus b. And when I wrote it all out, I just did my repeated multiplying and, repeated powers are multiplication. I wrote it all out, and I got x to the a multiplied by x to the b. So when I started with a plus, notice I went up, I got out a multiply. So it's kind of cool, right? That first rule sort of says exponential functions turn addition into multiplication. It's like it goes up the order of operations, or I've heard it said it cheats the order of operations. Like you start down here and you wind up here. Let's look at the second rule. Same exact thing. It takes us from this level to the top level. If I put a multiplication inside my exponent, a times b, I wind up with a power out, an exponent. I wind up with an exponent of an exponent. So x to the a times b becomes x to the a all raised to the b. I wind up in the top level with an added exponent on my exponent. So I thought that was worth pointing out. I think it's kind of cool how it all just fits together so nicely. And this is why mathematicians sort of made all this system to kind of work, so it's logical and pretty. Oh yeah, I have it here now. Here I have it, addition becomes a multiplication, and a multiplication becomes an exponent. But you also better believe if I have a subtraction in here, it will become a division here. And if I have a division in this one, in the second rule, it'll become, again, another exponent, except with a 1 over. And if I look at that, here it is. So if I have x to the a minus b, inside my exponent, notice it goes up the order of operations and becomes an x to the a divided by x to the b. My subtraction turned into a division, as if by magic. Okay, and if I put a division into the exponent, x to the a over b, I get another exponent. I go up again, one level, right? So x to the a raised to the, now here I have to remember my little 1 over b, like we looked at a minute ago. But anyway, that's all I got. So, follow your nose from elementary school arithmetic, And I think these two rules fit very nicely into a system here, as you can see with the order of operations. So thank you.